Thank you for joining us again. We're looking at Chapter 9.3, Simultaneity, or Simultaneity, however you want to pronounce it. We're following the Queensland Physics syllabus and the textbook done by Walding. There's a nice little joke there on the top there about trying to prove Einstein wrong. All right, let's get into it. So, let's have a few things to get our minds thinking. In war movies, the officer will often say, or whoever's in charge will often say, synchronise your watches before going out to a firefight of some sort. Why do they do this? Basically, in a war, you need to time things so things happen at the same time and different elements support each other. So you might want some fire support to happen right before the attack goes in, but you need the fire support to stop right before the attack goes in. Otherwise, people start dying from friendly fire. You want to avoid that. So hence, everybody starts off with their watches totally synchronized. And what you usually find is that when you're on operations for a while, you synchronize everyone's watches at the start, and usually they pretty much stay synchronized for the whole exercise or operation or whatever you're doing. Now this next bit, these next two, that's a little bit different. When you poke someone with a meter ruler, do they feel the poke at the same time as you push? So think about those wooden meter rulers you often see in high schools and stuff, or a stick or whatever. You poke someone, and pretty much as you poke them, they feel the push. Now, if you had a really, really long stick and you poked them, you would expect the same thing to happen. Let's say your stick was like, 10 meters long. As you push it, they would feel the push as you put the pressure on one end of the force on one end of the stick. But let's think about a really, really long ruler that's a light year long. If you push on one end of that ruler, and let's say, for example, that you're standing here and you've got your ruler and it's 1 light year long, and your friend's over here on the other side of the classroom, it's a really, really big classroom, and when you put a force on one end, you're pushing, will he feel that straight away, he or she? Will they feel it straight away? Have a think about that question. If they feel that straight away, then the force that you have applied has effectively travelled a light year instantaneously. Is that possible? And the answer is no, it's not possible, because nothing can travel faster than the speed of light. That force cannot travel faster than the speed of light and reach your friend on the other side of your really, really big classroom instantaneously. So how long would it take that force to reach the other side of the ruler? And the answer is it can't travel faster than the speed of light, so it's going to take at least a year for that force to get from one end of the ruler at the start here to the other end to push your friend. So it would take at least a light year for that pressure wave, that energy to pass through that ruler from one end to the other. That's a bit of a thought experiment there for you. All right, what are we looking at today? We're going to look at whether things occur simultaneously, and we'll describe what simultaneity actually means, because it's very, very important for relativity. All right, let's have a look at some examples here. Let's assume you're standing on a school ground and you hear that like the recess bell goes off or the lunchtime bell goes off, and there's more than one bell in the school usually. If you're standing right in the middle between the two bells, not like old Millhouse there, let's say you're standing here and your distance to one bell versus the other bell is exactly the same, you would hear those bells at the same time. But what's the likelihood that you're standing exactly between two different bells? If you stand, for example, over here closer to one bell than the other, then the time it takes that sound to reach you from the closer bell, that will be shorter, whereas the sound from the other bell has longer to travel to get to you, and hence you wouldn't hear them at the same time. All right, and that intuitively makes sense. Your sound travels at 346 meters per second, I think it is. Right? It takes time to get from one bell to another. And if you're in a large school and the bells are a long way away from each other, then you should, if you listen closely, hear the difference if they're far enough apart. And that's the idea of simultaneity. Things don't necessarily happen at the same time. We know that these two bells will ring at the same time because they're probably on a timer of some sort and they will go off at the same time. but it takes time for that sound to actually reach us and for us to hear the two events. Here's another example. Think about it at the athletics carnival. So you're sitting up in the stands and you see the starter pistol go off, as in you see like a puff of smoke from the starter pistol, and then you hear the sound of the actual bang of the pistol going off. You don't hear and see these events at the same time. So hence, they are not happening at the same time with respect to you. If you are the starter, like Mr. Burns there, or you're like Homer standing there right next to him, you will hear the sound and see the puff of smoke at the same time. So those events are simultaneous for you. But if your frame of reference is sitting way up in the grandstands or way down the other end of the starting track, they do not happen at the same time. Hence, they are not simultaneous events from your point of view, from your reference frame. And that's the idea of this simultaneity. All right? We assume two events may be happening at the same time, but they may not appear that way from our frame of reference. So, that's what this bit here explains. Assuming the sound and the puff of smoke are generated at the same time at the pistol, which they would be simultaneous events at the starting point of the race. However, if the sound's got to travel 100 metres to the timekeepers at the other end of the track, it travels at a certain speed. The light from the puff of smoke travels at 3 by 10 to the 8 metres per second, which is a lot faster than what the sound travels at. So the timekeepers do not see those two events as being simultaneous because it doesn't happen at the same time for them, even though we intuitively know it's happening at the same time. Here's another example of it. Think of these three locations, the yellow, blue, and grey dot, and there's two events that are happening, the red dot and the green dot, and you can see them expanding. So right now, the yellow dot has received both of those events. Right now, the blue dot has seen the red event, and the grey dot has seen the green event, but it takes time to see the other event, and the green and red event are only being seen now by the blue and grey dot. It takes time, and these lines here represent how that's actually occurring. You might want to play that a couple of times and just have a look at that animation and just get that one, just understand it fully. It'll reset now and do the same thing. Notice those lines underneath them show you the length of time that they've experienced that event. And it's different from all points of view. From our reference frame, we know that the red and green event are happening at the same time. The yellow dot sees them happen at the same time, but the blue and grey points do not see them happening at the same time. That's simultaneity. Here's another example of the same sort of thing on a moving train example. On the left-hand side there, the front and back of the train is struck by lightning at the same time, and you're equally distant away from them, so you see both of those shockwaves at the same time. That's what the left one's showing us right there now. But the right-hand image is a bit different because the train's moving. We know that both the front and rear are happening at the same time because we can see that from our point of view. But the blue sort of wave appearing out is how that propagates out through space and you see it. And if you're sitting on the train, you can see that the red seat that lights up on the train there, the two events do not appear to be happening at the same time. As in, you're travelling forward, you're travelling into the front shockwave and away from the rear event shockwave, and hence they don't appear to happen at the same time. If you're sitting on the train, it would look like the front got struck by lightning a fraction before the rear got struck by lightning. That's simultaneity. Here's another representation of the same thing as we warp space and time as velocity changes, and this is just another way of representing it. The grid represents almost like space-time, as this event's occurring in space-time, and we're travelling at different speeds of light. So it's one way to sort of visualise what was going on in those previous examples, even though it looks a bit weird. Okay, here's a good example. So we've got a light pulse that starts on the train, That's this bit here, the light pulse, and obviously it will send out light in both directions. And there's almost like a sensor at each end of the train carriage, and when the light reaches that part of the train carriage, it will open the doors. I don't know why it opens the doors, it just does. Just go with it, all right? Stop asking questions. So we've got two observers. One is a person standing on the train, and the other one is a person standing on the bank watching this happen. So let's think ahead about what's likely to happen here. If you're standing on the train, perhaps you're standing in the middle where the light beam is, the light pulse starts, you would see both light beams head off in either direction and reach either end of the train because your reference frame is inside the train and that inside the train to you is not moving. So you'd see the light reach both ends at the same time. You would see both doors open at the same time. But go back to that example I had a couple of slides ago of the train getting struck by lightning. If you're on the bank, things don't work that way. So, observer on the train, both doors open at the same time because the speed of light is constant, it's travelling the same distance. It still has this distance versus this distance, it's the same. Both doors open at the same time. Now let's think about old mate standing on the bank here. That's not what he sees happening. As this event occurs, the train is moving forwards. That's to the right on the screen there. And what's happening is this front door is moving away from the event while the rear door is moving forward towards the event. So as that event occurs, the rear door is speeding towards it to catch up to it. So the person on the bank will see the rear door move up and meet the light beam, and hence it will open first. And we'll see the front door move away from the light beam, so it takes extra distance for that light to travel, and hence the person on the bank sees the front door open after the rear door. That's the idea of simultaneity. Depends on your reference frame and where you're standing. You'll see two different things. The laws of physics are still the same, but what you're experiencing is not happening at the same time. Much like the two bells ringing at school, you're right next to one, you'll hear it go straight away. If there's another one more than 100 metres away across the school, you'll hear it a little bit later after the first bell goes off. Even though you know they're electronically controlled and they should go off at the same time. We've got some animations there which show similar sorts of things. I'll just let them play, have a look at it. Alright, it's kind of like we're synchronizing clocks there. Method 1 on the left hand there. It's like you set a signal from one ship to another, and that's what the blue line represents. The signal from one ship to another and then to each clock. It reaches the rear clock first because the rear clock is moving up towards it, whereas the front clock's moving away. Or another way to think about it, the clocks in the other image don't necessarily synchronize because they start off in the center of the ship. One moves away, so it's traveling at a slower speed, whereas one moves faster towards the front of the ship, and hence their clocks are not necessarily the same time. A little challenge there, imaging mirror. I encourage you to pause the video, have a look at that one. The problem is as you approach the speed of light, time starts to slow, and at the speed of light, time would appear to stand still to observers outside your reference frame. There's another little flashlight on the train example to have a look at, and a nice little XKCD cartoon. Once again, I do recommend you go and have a look at xkcd.com. Alright, let's have a look at our understanding. You see two lights flash at the same time. Are they simultaneous? Have a think about your answer. You need to be equidistant from them. However, there's a little asterisk I've put on that answer there, number 4. It depends on gravitational fields. Because when Einstein did his work on general relativity, he discussed how gravitational fields can warp light, and they warp space-time, which affects how long it appears light takes to get different places. So, with no big gravitational fields, if you're equidistant from them, you'll see them as simultaneous events. Here's a good question for you to have a go at. You can pause the video and read that cartoon as well if you like, but let's have a look at what we're doing. So which is quicker, a light beam travelling halfway around the surface of the Earth to the other side, or a sound wave travelling through the centre of the Earth? Now I said before that the speed of sound was about 346 meters per second, but through a solid such as Earth, it has a different speed. So what do we know? We know that the velocity is the displacement over the time. You can work out the displacement of the sound wave because it's going through the center of the Earth. You know its velocity, hence you can work out the time. You know the circumference of a circle from that equation from middle school mathematics. So hence you can work out the distance or the displacement the light beam has to travel. We know the speed of the light is 3 by 10 to the 8 meters per second. Pause the video and see if you can work out which one's going to get to the other side of the Earth quicker. Here's our Earth. You're standing over here. It's like you've got your mate standing on the other side of the Earth here. Do you send sound directly through, or could you send a light wave, a light beam around, if you could bend it around the Earth like that? And here's your answer. The light beam gets there much, much quicker. It takes that long for the sound wave to get through. We have to work out the distance the light's got to travel. Travels at 3 by 10 to the 8th. And that number went in there. 0.03 seconds. So much, much quicker. Alright, that brings us to the end of this section. Have a go at the check your learning questions. Have a look at the next section before you finish up. And I do encourage you, if you've got your login to Oxford, check out this particular paradox here to learn a bit more about it. Alright, thanks for coming.